Hey everyone. In this lesson, we'll learn how gradient descent helps a model learn from data. You'll see how we start with initial values, measure the error, and then repeatedly update our parameters to make better predictions. By the end of this lesson, you'll understand how gradient descent is implemented in the code and how it works step by step in linear regression. All right, let's begin. Let's move on to step 1. Here we load all the libraries that we need in our code. We need 4 libraries. NumPy, or numerical Python, is a library used for working with numbers, arrays, and mathematical operations. It is basically the foundation of almost all machine learning and data science code in Python. Matplot. This is simply a library that gives us plotting capabilities. Copy. This library allows us safely duplicate objects so changes to one does not affect the original. And finally, the math module, Python's built-in module, which provides common mathematical functions and constants. These 4 libraries together will support us with all numerical operations and utility functions needed in our code. Okay, let's move on to step 2. Step 2 is all about loading data. First, we need to define and load our training data. In this example, we will use car mileage and car price data to train our model to predict a car's price based on its mileage. This dataset is used to evaluate our model. It contains the true price of each car along with its corresponding mileage. Since our training set has 8 examples, naturally the value of m in our calculations will be equal to 8. Remember, the data represents the ground truth. Without data, there is no learning. And with poor quality data, the model will learn incorrect or biased patterns. So pay special attention to data when building and training a model. And make sure you can trust the origin of the data when using any AI model. Now let's look at the code that defines our training data and see how this data appears on a chart. For simplicity, we have defined the data directly in the code using arrays xtrain and ytrain, so it is easier for you to see. Each index here represents one car or one training example. In practice, data usually lives outside your Python file and can be loaded by using the load data helper function. In learning setups like ours, data is sometimes loaded inside the function, basically to keep examples self-contained, avoid passing too many arguments, and to focus on understanding the algorithm, not file handling. In real projects, however, data is often loaded once, outside the function, and in those cases, we use the load data helper function to load our data. It's also good to know that most common data file types typically are CSV files, text files, JSON files, and NumPy files, or files with .npy extension. All right, now let us move to step 3. Step 3 is about building our cost computation function. We call this function compute cost. The job of compute cost is to give us one single number that tells us how well our linear regression model fits the data. Let's walk through the compute cost function together and see how this function works. Don't worry if you're not an expert in Python. This is easy and could be a great starting point for you. All right, from the code, you can see that the first line basically defines the function, and the function name is compute cost. In line 2, we store how many data points we have in our data set. In this example, we have 8. Line 3 initializes the total cost, also called the total error. Basically, it creates a variable to accumulate the cost and initializes that variable to 0. Line 4 processes each training example one at a time. Line 5 computes the predicted value for training example I using the linear regression model. In line 6, the cost computation is done. It basically computes how far the prediction is from the true value. In line 7, we accumulate the cost. Basically, this line keeps adding the squared errors from all training examples. In line 8, we finalize cost calculation by averaging the total cost and dividing that by 2 to simplify gradient calculations. And finally, in line 9, we return total cost or total error to the invoking code. Now that we know how to compute cost, let us move on to step 4, which is building our gradient computation function. We call this function compute gradient. Let us walk through this function and see how it works. As you can see, the first line defines the function with the name compute gradient. Line number 2 stores number of training examples. Segment 3 initializes the variables. These are the variables returned to the invoking code. Line 4 loops through the data, processes each training example one at a time. Line 5 predicts the output for the training example for our linear regression model. Line 6 calculates gradient descent for W for example I. Line 7 adds that gradient descent for W to total gradient descent for W. Line 8 calculates gradient descent for B for example I, and line 9 adds the calculated gradient descent for B to total gradient descent for B. Segment 10 finalizes gradient descent calculations, and finally, line 11 returns the total error to the invoking code. All right, now we are also done with gradient computation function. The next step is to find the optimal values of W and B for our linear regression model. Let us go through this function and see how the code works in our gradient descent function. In line 1, we store the number of training examples as before. In segment 2, we define the lists or the containers to store the cost J and W at each iteration. Segment 3 makes sure global W is not modified within function. Segment 4 calculates gradient and stores new W and B parameters. Segment 5 saves cost J and prevents resource exhaustion. Segment 6 saves W and prints cost every 150 iterations. And finally, in line 7, we return the arguments. So now we have built all the functions that we needed. So the next step is basically run our gradient descent function and see what we get as results. Here we see the results after running gradient descent on our car price dataset. On the left, the code initializes the parameters and runs gradient descent for 1,500 iterations with a learning rate of 0.01. Basically, our alpha here is 0.01. As training progresses, the cost steadily decreases, which tells us the model is learning and improving its predictions. On the right, we see the final fitted line plotted against the training data. Each red X represents the actual car prices, and the blue line shows the model's predictions. The learned model is shown as f of x equals minus 0.13x plus 2.84, which means car price decreases as mileage increases. This matches real-world intuition and confirms that gradient descent successfully found a good set of parameters. Now, let's use our trained model to make an actual prediction. We take a car with 53,500 miles, which corresponds to 5.35 on our x-axis, since mileage is measured in tens of thousands. By plugging this value into our learned model, the model predicts a price of about $21,448. On the chart, this prediction is shown by the red X placed directly on the regression line. This confirms that our model is not just fitting the training data, but can also make reasonable predictions for new unseen examples. This is exactly what we want from supervised learning. Learn from known data and accurately predict future outcomes. So this is gradient descent, a simple but powerful idea that allows our model to learn by gradually improving itself step by step. By following the slope of the cost function, we found the best values for our parameters and built a model that can make real predictions. In the next lesson, we will learn regression with multiple inputs, where a model uses more than one feature to make even better predictions. Great job following along, and I'll see you in the next lesson.